stress, and stress is really just in its most basic sense is just force per unit area. So if you imagine here we have some prismatic member that we're applying an axial force to. In this case we're putting it into tension, or we could be applying a compressive force here, putting it in compression, but we're looking at an axial force here, and we are asked to find what is the normal stress at any point in this member. So the way that we do that is we section the beam at some point. Basically, we just pass a virtual cut through it, like we've been doing in statics videos, if you which you should be familiar with by now. But when we do that, we basically just reveal a cross-sectional area. Here, let's draw this on. We show a cross-sectional area of one of the internal faces, of that virtual cut that we've done. And when we do that, we think that when we want to draw a free body diagram for this, you can see that for let's say for this section of the beam here, we're going to have the force P pulling in one direction, and we need to just cancel that out with an equal and opposite force. But the way that we do that is we just assume that the force is distributed evenly across this surface, giving us a stress actually. So we call that stress here lowercase sigma, and that stress is just equal to, like I said, the force per unit area. So we're just going to have P over A. And we call this a normal stress because the stress is acting normal to this surface that we've, to this cross-sectional area, or this surface that we've kind of virtually exposed. Now, if our applied force here is in newtons and our area is in meters squared, then our stress here is going to be in units of newtons per meter squared, or that's also called pascals. But usually in mechanics of materials courses, we're going to be working in the range of kilopascals, megapascals, or gigapascals. And in mechanics of materials, we're going to be making an assumption to simplify the analysis that there is going to be a uniform distribution of the stress over the whole cross-section of the member, no matter where we slice it. Now, in reality, the closer that you get to an applied force, the less true this gets. If you imagine that we have this applied force here right at this point on the face, then a point on the face right over here in the corner isn't actually going to be under a whole lot of stress, because all the stress is going to be concentrated kind of right around there. But the further you get into the beam, the more distributed, the more evenly distributed it gets. But we're going to make the assumption that it is uniformly distributed everywhere through this beam. And lastly, for problems involving normal stress, we're going to be assuming that the axial forces here are being applied at the centroids of the cross section. So you'll notice I did draw this right at the center of the square here. This is called centric loading, and this will simplify our analysis. And at this level, it will only be having centric loading. If we're not applying them right at the centroid of this surface or the cross-sectional area, then that will be called eccentric loading. And we'll run into that in later videos, but for now, just don't worry about that because it's going to be developing internal moments and that sort of thing. But right now, we're just talking about normal stress. So let's imagine in this case that we actually have some dimensions. Let's take our frontal view of this face here, and let's throw on, let's say it's 50 millimeters by 50 millimeters. So that means that we're going to get a cross-sectional area of 2,500 millimeters squared. And let's give ourselves an applied force here of, let's say, 100 kilonewtons. So when we want to go calculate for our normal stress here, that's just P over A. This is our applied force over a cross-sectional area of the member. We're going to get, this is 100 kilonewtons over 2,500 millimeters squared. And that's going to give us 0.04 kilonewtons per millimeter squared. Now that's a pretty weird unit because I know that newtons per meter squared are equivalent to pascals, but looking at this, it's not super obvious about it. So if we just do a unit conversion, we're going to find that this is equal to 40 million newtons per meter squared, which is equal to 40 million pascals. And if we have 40 times 10 to the 6 pascals, we're going to get 40 megapascals. So let's say that we have 40 times 10 to the 6 pascals. So that is also equal to 40 megapascals. Or sometimes you might be asked to give your answer in kilopascals or gigapascals, so we could just make that conversion. This would just be divide this by 1,000, we would get this is also equal to 0.04 gigapascals. Or if you go the other way, multiply it by 1,000, then this would also be equal to 40,000 kilopascals. About stress-strain diagrams, because these are fundamental to the study of mechanics of materials, but they're often misinterpreted by students when they're first introduced. So what we're looking at here is two typical profiles for stress-strain diagrams. On the left one here, we have just a typical profile of a ductile material. For example, that could be structural steel. And on the right here, we have a typical profile for a brittle material, which, for example, could be cast iron. Now, how this works is if you're taking mechanics of materials in university, part of your course will be going to the lab and seeing the testing apparatus. But basically what you do is you take a rod, let's say for the structural steel, take a rod of structural steel, and you place it in this testing apparatus that will sort of slowly and incrementally apply more and more tensile force to it. And then as it slowly applies more tension, the computer basically spits out this graph, and that's how you get the stress-strain diagram. Now, when students hear that we're incrementally applying a load, an increasing tensile load, then you kind of immediately jump to the conclusion that, well, it's the load itself is the independent variable and the strain that's resulting is the dependent variable. And so we often jump to thinking, well, if we're applying a load which is independent, then we look at this here and we see this stress, and we think that this stress must just be like the incrementally, the increasing load times the cross-sectional area, making this the independent variable and making this the dependent. But that's not how we draw graphs, because we always draw the independent variable on this side and the dependent variable on this side. So don't jump to that conclusion. A lot of people do, because that's not right. So what's really happening is when we're incrementally growing the tensile force or increasing the tensile force in the member, it's that applied force that's actually causing strain in the member. So when we increase the tension, we increase the strain, and that strain actually causes stresses to develop in the material. So these stresses here is not just the force times the area, the applied force times the cross-sectional area. These are the internal stresses that are resulting from the strain, which is resulting from the applied load. So the strain in this sense is the independent variable, and the internal stress in the member is the dependent variable, which is fully dependent on how much strain there is. So that's just a huge misconception that a lot of people get wrong when they first see these diagrams, and I hope that I articulated that clearly enough. So let's focus in here on the first section of the graph from 0 up until we reach sigma y here. And this is the sigma y here is the yield stress. So if we apply some tension to this member and we get a corresponding strain that's going to result in less than this yield stress, if we stop loading it there and we unload it, all of the strains actually are going to disappear. So we basically have stretched out the material, and then as long as we don't pass this yield stress here, when we unload it, the material is just going to shrink back down or kind of rebound back to its original length. And we call that elastic behavior or elastic deformation. And in this region, Hooke's law applies. And for those of you that, if that's new to you, Hooke's law here is stress is equal to capital E here, this is the modulus of elasticity, times the strain. So there's a linear relationship between stress and strain in this first section here, so long as the material has not yielded. Now if we keep applying our tensile force here, and we get a strain that's going to cause us to reach this yield and then keep going, or this yielding stress and then keep going, what happens is in this region we get yielding, and basically what's going on is we get extreme like a significant elongation of the member with actually very little extra applied load. So going back to this first section here, where I said if we load the beam, we're going to follow this profile going up and up like that. And if we unload it, then we follow the exact same profile back down all the way to 0 strain. Now, if we apply this load such that we get a strain that takes us past this yielding stress, or at least up to this yielding stress, and we get yielding, if we unload the applied force in that region, basically what it's going to do is it's going to start here the plot, and the plot kind of it adjusts. It'll shift over. It'll follow this same slope here, but when we unload it, the stress strain profile actually goes down like this, and it won't return to 0 strain because I've said we've actually reached that. We've reached the first part of our plastic deformation now, and some of these strains will now be permanent. So if we reduce the load down to 0, we'll get stuck with some of these strains and this plastic deformation, and then when we reload it again, now it's going to follow this this pattern here on the stress strain curve when we're applying that incremental tensile loading. Now, if we keep applying even more of the loading in this testing apparatus, and we make it so we have a strain that's actually taking us past this point, and we're into this region now, we get this region and we call it strain hardening. So you can imagine if we loaded it up until maybe here, and then when we go to unload, we take off some of that, we're going to get this this profile like this, and when we unload the applied force on this member, the stress strain diagram falls back down to here, and we're stuck with even more deformation than before. But then when we go to reload this member, we go up this way, and we've kind of created this region that will actually now sort of act elastically to the point where we come back to this amount of deformation, but we can actually achieve a much higher internal stress that actually approaches, we get closer to our ultimate stress. So if we push it even further, we get to this last point, the top of our curve here, which is our ultimate stress. So the region where the curve was increasing again was called strain hardening. And if we apply a load which results in this strain, which then results in us reaching our ultimate stress, that means we've applied our ultimate load to this particular member or specimen. And if we keep loading it past that, we'll get a thing that's called necking. And that is basically the member itself will start losing cross-sectional area and really stretching out. So it kind of starts, if it started like this, which is a nice, uniform cross-section, it actually gets really weak in one area like this, and eventually we'll come to this point, and this is it'll snap, and this is called our breaking stress, where the member will finally catastrophically fail. And if you remember from some of the previous videos, we were talking about the ultimate stress of a material is either the point where it breaks itself, or where it loses the ability to maintain that level of or to support that load. If we passed our ultimate load here and kept going with a load, and then we suddenly unload it, or not suddenly, but if we unload it, we'll follow this profile back down. When we unload the member, we'll follow this profile of the stress strain curve, and then when we come back up again, if we reloaded the member again, we're not even going to get to this point again before we get closer to that breaking stress. So that's a little bit. So that's kind of just like an introduction to how how the stress strain curve looks for ductile materials and the different major regions of it. So the elastic deformation, yielding, strain hardening, and necking. And again, wanting to make sure that you guys get that we are applying that tensile force which causes the strain in the member, and that strain is what's causing this this internal stress here as the dependent variable. So that was all for ductile, but for a brittle material, it's actually quite a bit simpler. We just we don't have all of the signs of yielding and necking, where we'll just get a sudden break when we apply a force that gives us the right amount of strain. That will be the ultimate stress, and it is also the same. The ultimate stress is the breaking stress. So we just get basically catastrophic failure without any warning. So that's just something to be wary of if you're designing something that's made out of cast iron or another brittle material, is you won't get the same warning signs as if it was made out of a ductile material. Alright, so I hope that explanation helped you guys. It can be really frustrating if you don't understand what is the dependent and independent variables in these graphs and where they come from and how they work. So Hooke's law is the relationship between normal stress and normal strain for members that are behaving elastically. So if you remember from the last video here, we were looking at the stress strain curve. In this case, it is for a ductile material. And when we're saying the material is behaving elastically, we mean in this region here before we've reached an internal stress here that's equal to the yield stress. And just to recap is if we load a member with a slowly increasing amount of tension, we're going to be getting more strain building up in there. And as the strain increases, the internal stresses increase. And as long as we keep loading with our axial force here, the strain increases and the stress increases. But if we don't actually pass the yield stress here, when we start unloading the beam, the stress strain curve kind of goes back down on the exact same path here on this linear section, and we return back to zero strain basically. So we'll stretch out the member, and then when we unload it, it completely goes back to its original length. So that's what we mean with elastic behavior, and Hooke's law is for members. Hooke's law holds true for members that are experiencing this elastic behavior. So this capital E here is the elastic modulus, and it's also called the Young's modulus. And it's actually the slope of this straight part of the stress strain curve in the elastic region. And for this unit, or for this equation to work out, its units are the same as stress, because if you remember, strain here is unitless. So if we have the expression for Hooke's law, which is the normal stress is equal to the elastic modulus times the normal strain, well, we also know that the normal stress can be written as, or is the applied load over the cross-sectional area of a member. And we also do know that the strain, the normal strain, is the displacement, that incremental displacement that we find in the member over the initial length of that member. So if we plug these into the original equation here, or into Hooke's law, we basically get P over A is equal to E, so elastic modulus times delta over L. And we can rearrange this for delta here, and we'll find that we get this expression for delta where it is equal to PL over AE. And we can now determine the deformation in a member that's subjected to axial loads if we just know a little bit of information about it. So let's go ahead and solve this example then. So we need to first calculate the cross-sectional area of this member. So we have A is equal to pi r squared, which is equal to pi times 10 millimeters squared. And if you just do that, that's equal to 314.16 millimeters squared. Now we have everything we need. We have A, we have P, we have L, and we have E. And E will pretty much always just be given to you in an equation, and when we're dealing with steel, it's often going to be 200 gigapascals. So if we just plug in our equation, we can figure out what type of, how much displacement we're going to be getting, or elongation that we're getting in this, this rod here that's subjected to this axial load. So if we just plug all these in, P here is 150 kilonewtons, times L, which is 500 millimeters, and down on the bottom we have our area, so we have 314.16 millimeters squared times E here, and this is 200 gigapascals. Now if you remember from previous videos, so like if we're trying to calculate this, we're running into some weird units here, but if you remember from some of the previous videos, we determined that gigapascals is actually the same thing as kilonewtons per millimeter squared. So what we can do is we can change this from gigapascals to kilonewtons per millimeter squared. Now when we check these units, these millimeter squareds cancel out, kilonewtons cancel out, and we're left with millimeters. So if we run that calculation, you just get this delta here is equal to 1.19 millimeters. So to get torsion in a member, we basically just need a pair of twisting couples. And if you imagine that we have a rod here that has a rigid connection to a wall, if we apply a torque on one end, then the wall is going to have to provide that equal and opposite torque, so the opposite sense and the same magnitude to keep this thing in static equilibrium. Now there's some similarities here to the material properties as when we were discussing axial loading. So in the case of axial loading, if we put this member into tension, we actually got some deformation of the rod and it stretches out. Well, when we apply this torque here, we're also getting a type of deformation, but it's basically just twisting in place but keeping the same shape. So if we had a point here on the right-hand side of this rod, and we drew a straight line to the corresponding point at the other end of the rod there like that. When we apply this torque, basically the end of the rod is going to be turning and it'll be deforming in that sense. And then depending on the size of the torque, the final position of this point might end up somewhere like this. And then we can draw a straight line back to its original point. And if we take this angle here out from the axis of the rod, then we get what is called the angle of twist in units of radians. And as long as we're only experiencing elastic deformation in the rod, we can use this formula to describe the angle of twist. Where T is the internal torque, usually in kilonewton meters, L is the length of the member, J is the cross-section's polar moment of inertia, and G is the modulus of rigidity, and usually for steel we're going to be using 77 gigapascals. And in this expression for the cross-section's polar moment of inertia, C2 is just the outer diameter of a shaft, and C1 is the inner diameter of the shaft if it's hollow. So if it's not hollow, this just becomes 0, and these are both in meters. Alright, so what this formula is showing us is that the angle of twist is proportional to the internal torque. So if we apply a bigger torque, we're going to get a larger angle of twist. And the angle of twist is also proportional to the length of the member. So if we take a cross-section halfway along this rod, then we're going to find out that its angle of twist is going to be half as large. And that's really important too for the next point, is that the actual face of the cross sections that we expose does not get distorted. So what we say is that plane sections remain plane. So if we draw an image here of the cross section inside the rod, and we're gonna if we draw a green line on that goes horizontally and a blue line here that goes vertically, then this is the original undeformed position, and so we can place that right here where it connects to the wall. And when we twist it at the end of the rod here, basically what we're saying is the angle of twist that we're getting is going to be equal to this angle here, phi. So it has rotated like that, and it actually hasn't deformed. We're not getting something that looks like this. So it is just staying undeformed like this. This is what we are getting. Yes. So we don't get any sort of change in the deformation as we go radially outwards. So what that means then is if we look at the cross section halfway down the member, like I just said, we would expect an angle of twist of half as much. So if we place on our face, basically the deformation that it's experiencing is just like that. And we could draw on these cross sections anywhere along here, and you'll just notice that it is proportional. The angle of twist is proportional to the length that we're traveling down this member, so long as we're not changing the internal torque. And if we do change the internal torque, or we do change the cross section's polar moment of inertia, or we change materials or something like that, we actually treat this very similar as we did to problems under axial loading, where we just take the sum of each part, and each part is defined as anytime there's a change in any one of these variables and we just sum those guys up. So if there was another applied torque halfway down, then we'd have two sections with two distinct internal torques. Or if if one half of it was hollow and the other half wasn't, then we'd obviously have to change this, or the diameter changed, we'd have to change this. Or if half of the member for some reason was one material and then the other half was the other material, then in those cases we'd all have two sections. Obviously we could have as many sections as the problem presents. So let's attach some numbers to this example and see what we get for the angle of twist. Let's say we have a length of 0.5 meters, a diameter of 60 millimeters, and then we'll have a modulus of rigidity of 77 gigapascals. We'll say this is steel. So in order to use this formula, we're going to need to calculate for J. And so for J here we have, this is just equal to pi over 2 times C2 to the power of 4 minus C1 to the power of 4. Now I said before that C2 is just the outer the outer radius, the distance from the axis to the outside of the member, so that is that C2, and then C1 is only for hollow members, so if this is solid, then C1 becomes 0. So we have pi over 2 times, well, the radius here would be 30 millimeters, and that would give us 0.03, let's put in the units there, that's meters, and that's to the power of 4. So this is going to return us, the number is 1.272 times 10 to the minus 6 meters to the power of 4. So that is our cross-section's polar moment of inertia. Alright, so let's go and plug everything into our formula here. We only have one section because nothing is changing along the length of the member. So we're just going to have our internal torque, which is 5 kilonewton meters, times the length, which is 0.5 meters. And we're going to put this all over our moment of inertia down here. So this is 1.272 times 10 to the negative 6 meters fourth, and then times our modulus of rigidity, which we're saying for steel here, I didn't write that on. We'll say for steel it's going to be 77 gigapascals. So we'll write that in, 77 gigapascals. Alright. Now we do need to be kind of thoughtful with our units here just to make sure that we actually end up with the proper units of radians here where everything will cancel out. So the way that that I would like to visualize this is 5 kilonewton meters is just 5 times 10 to the power of 3 newton meters. 3 newton meters times 0.5 meters. And then we have this thing, we'll keep the same thing on the bottom, we'll have 1.272 times 10 to the negative 6 meters 4. And then times, I might convert this into pascals, so we'll just do 77 times 10 to the 9. Let's do kilonewtons per meter squared. Or sorry, not kilonewtons, this is newtons per meter squared. Newtons per meter squared. Alright. Now if we look at this, we're going to have this newtons here. We'll cancel out with these newtons here. And then we have 2 meters on the top, we have 4 meters here, and then we have another 2 meters down here. So these are all going to cancel out. And we're actually going to get rid of all of these units, and we'll just be left with radians. So we can simplify this a little bit. So we have 5 times, it might even be easier just to split this out, times 10 to the 3 times 0.5. And this is over 1.272. Now if we look at this, we have 10 to the minus 6 times 10 to the 9. So that's going to leave us with the 10 to the 3. So we'll bring that on the bottom. So we have times 10 to the 3. And then we also have that 77. So times 77. So we look at this, we have 10 to the 3. We can cancel that out. And we're left with just 5 times 0.5 all over 1.272 times 77. And that's going to give us 0.0255 and that number is in radians. So that is equal to our angle of twist. Now if we did want to figure out what that is in degrees, if you prefer that, then we can just say that we have, we can do the conversion, 0.0255 radians times 180 degrees over pi radians. And we'll find out that the angle of twist at the end of this rod here is going to be equal to 1.46 degrees. At the free end of this shaft that's being applied, that has this torque applied to it, and you'll notice that the shaft here has two distinct cross-sectional areas. So the way that we do this is we use our angle of twist formula, which is equal to the sum here of all of the parts, and the parts are where any of these change. So we have TL over JG, and each of those has that little I there representing each of the parts. So if we look at this, we're saying that this whole thing is going to be made out of steel, so it will have a modulus of rigidity of 77 gigapascals. So that is constant throughout. The torque, the internal torque, is going to be constant throughout, and the thing that's changing here is J, which is our each of the cross-sections polar moments of inertia. So what we want to do, if we define this section, the little section as section 1 and the big section as section 2, then what we want to do is we want to figure out what J is for section 1 and also for section 2. So the formula that we use for the polar moment of inertia is just pi over 2 times c2 to the power of 4 minus c1 to the power of 4. Now that was from the previous videos, where c2 is basically the distance from the center, from the axis here out to this outer surface of the rod. And C1 was, if it's a hollow member, that's the distance to the inner surface. So this is a solid member, so C1 is actually just going to go to 0. So for J1 here we get pi over 2 times the radius, and the radius is 15 millimeters, but we want to write this in meters, so 0.015 meters to the power of 4. And that's going to give us 0.0795 times 10 to the minus 6 meters to the power of 4. Now we want to put it into units of 10 to the minus 6, because you'll see in a second when we plug it into this formula here that we're going to be able to cancel out a whole bunch of units, and it's going to be advantageous to us to have it in this 10 to the minus 6. For J2, we'll take the polar moment of inertia for section 2 here. We have pi over 2. Well, it's a solid member, so we know that C1 is going to be 0, so we'll have just the C2, which is the radius, so it's 30 millimeters, so we'll put that into meters, 0.03 meters to the power of 4, and that's going to give us 1.272 times 10 to the minus 6 meters to the power of 4. Alright, so now what we want to do is we want to plug these into our angle of twist equation. So we have our angle of twist, we'll do it by parts, so we'll do part 1 first. So we have 0.5 kilonewtons times the length of this section, which is 0.3 meters here. And this is all going to be over J here, so we have 0.0795 times 10 to the minus 6 meters to the power of 4 times our modulus of rigidity here, so times 77 gigapascals. Alright, cool. Now we'll add in section 2. So in section 2 we still have the same internal torque. We have 0.5 kilonewton meters, my bad. Kilonewton meters times the length here, which is 0.4 meters. And we'll throw this all over JG for section 2, so we get 1.272 times 10 to the minus 6 meters to the power of 4 times 77 gigapascals. Woohoo! Alright, so now if you remember from the last video, we showed that these units all can, if you write them exactly like this, so kilonewton meters times meters, divided by something times 10 to the minus 6 meters 4 times gigapascals, those actually all work out to canceling everything out, and you're just left with radians. So we can basically drop the 10 to the 6 meters 4, we can drop the gigapascals, and we can drop the kilonewton meters and meters. But only if it's written exactly like this. If we wrote this in newtons, then obviously this isn't going to work out. So if it's written with these units, we drop all that stuff, so we're just going to be left with 0.5 times 0.3, and then the bottom here we're just left with 0.0795 times 77. Makes our lives really easy if we're using this 10 to the minus 6 and all these other units. So then this side here we have 0.5 times 0.4, and this was all over just what's left over, 1.272 times 77. So if we simplify this a little bit more, we're going to find out that this first term here is equal to 0.0245 radians, and this second term here just works out to 0.0020 radians. And if we just add those up together, we're going to find out that our angle of twist, let's write it here, angle of twist is just equal to 0.0265 radians. Alright, so that is the angle of twist at this free end. And if you're curious and you want to figure out what that is in degrees, well, all we have to do is we just multiply it by our factor here, 180. So we'll go times 180 degrees over pi radians. And this gives us the angle of twist at that free end there of 1.52 degrees, right? So shearing strain can be represented with this expression, where for any cross-section that we want to consider inside of this member under torsion, rho here is going to be our distance from our radial distance out from the axis of the shaft. So if we're looking at the face here, it would be, for example, however far we want to go. We don't necessarily have to go all the way to the surface of the rod, to the outer surface, but if we do, then we call that C. But we could go a third of the way, or 2/3 of the way, or half of the way, or whatever, and that distance in meters is rho. We also have the angle of twist here in units of radians, and then we divide by the length to that cross section that we're looking at. So if we're going to the very end like this, then we'd be dividing by the length here of 0.5 meters in this case. And then those units, when we divide them out, gives us our shearing strain here of gamma in units of radians. So you'll see that there's a linear relationship between shearing strain and the radial distance that we go out from the axis of the shaft here. And also there's a linear relationship to the angle of twist. And for any given length L, we'll have a certain angle of twist, but this means that for that relationship between the distance traveled outwards radially from the axis, that our max shearing strain is going to occur when we have a maximum distance out from the radius, which is when rho equals C. And again, C just being the maximum distance that we can have from the axis there to the surface. Alright, so if we want to start calculating for shearing strains, then we're going to need the angle of twist. And we did this exact same problem in one of the previous videos, and so the angle of twist, we'll just skip through the equations here. So the angle of twist was 0.0255 radians. So if we want to figure out what the shearing strain is at a distance that is, let's say, 10 millimeters away from the center, so 1/3 of the way out to the edge of the rod here, then we'll have our shearing strain is just going to be equal to the distance away from the center that we're concerned about times the angle of twist divided by that length. So we're going to get 0.01 meters times the 0.0255 radians. And over that length there to, let's say we're looking at the surface here, which we are for that angle of twist, so divided by 0.5 meters. And when we punch that in the calculator, we just get the shearing strain is equal to 0.0051 radians. And that is, if you go out anywhere that radially out 10 millimeters from the center, then that's the shearing strain that we're going to be getting. If we wanted to take the shearing strain, so we can even put a little sub here, like 10 millimeters. If we wanted to take the shearing strain, let's say 2/3 of the way out, so 20 millimeters, we're going to be using the exact same formula. We have rho times the angle of twist over L. So for this part, we're going to have 0.02 meters times all that same stuff, 0.255 radians. And we'll divide that again by L because we're looking at the same section here with that given angle of twist. And when you punch that in your calculator, you just get 0.00102 radians. Now if we look and we want to figure out what the shearing strain is right at the surface, so 30 millimeters away, we're going to be getting, this is actually going to be our max because we're taking our rho to be C, and C is just the max radius there, so we have C times angle of twist over L, and when we drop that in we get 0.03 meters times the angle of twist, that was radians, and over 0.5 meters, and we're going to be seeing that that is equal to 0.00153 radians. So what you should be seeing now is that there's this linear relationship in shearing stress that correlates to our radial distance from the axis of the shaft. So where we doubled our radial distance here from 0.01 to 0.02 meters, the shearing strain also doubled. And here where we tripled it from 0.01 to 0.03, we tripled the shearing strain. So the last thing that that really comes of that is that there's an expression that we can use that is the shearing strain is equal to, so the shearing strain on any cross-sectional surface is equal to rho divided by C times the max shearing strain. So you might be able to figure out what the max shearing strain is, and then we can use that. So we have that right here actually, this is the max shearing strain. Then we can use that to just plug in to find out what the shearing strain would be at any distance from the axis here. So let's just take a random distance, let's say something like, let's go 23 millimeters away from the center. So we'd plug that in here as rho, so 0.023 meters over a distance over C here, which was 0.030 meters. And then we'd multiply that by our max shearing strain, which is 0.00153 radians. And when you crunch that, you're going to see that we're going to get 0.001173 radians. That's what you see here, and this was our discussion on shearing strain. And we learned that when we apply a torque on a rod, we get shearing strains on any of the cross-sectional areas if we were to kind of virtually section it. So in this case, we were looking at the shearing strains right on the end here, and we found that at a shearing strain of 10 millimeters away from the center, so 1/3 of the way out radially from the center, we were getting this shearing strain here of 0.00051 radians. And then when we went out 2/3 of the way to 20 millimeters, we were getting a shearing strain that was actually twice as large. And when we go 3 times the distance out, so actually 30 millimeters right out to the surface of the rod, we found our max shearing strain here to be 0.00153 radians, and that turns out to be exactly 3 times larger than this number. And that's what we would expect because shearing strain varies linearly with the radial distance away from the axis of the rod as we go out towards the outside and we approach that max distance there, which is the radius basically of the rod. So
I want to talk about shearing stress now, and shearing stress also varies linearly. And if you remember, actually, we have the relationship here. We have shearing stress, according to Hooke's law, is just equal to the modulus of rigidity times the shearing strain. And given that the shearing strain is just in units of radians, and this modulus of rigidity is usually given to us in gigapascals up here, that's going to give us a unit of gigapascals, or whatever variation of pascals, for our shearing stress. So if we want to figure out what the shearing stress is at the 3 points that we've already identified the shearing strain for, well, let's go and let's bring these down. So let's just drop them in here. All we have to do is, I'm actually going to write that. It's kind of hard to see that that actually says 10 millimeters. All right, cool. So in order to get our shearing stress, all we need to do is do strain times the modulus of rigidity. And up here, we have it for this problem is 77 gigapascals. So we're going to drop down here, and maybe let's just change the color. So all we're doing is we're just going to multiply this by G, multiply it by 77 gigapascals. And when you do that, 0.00051 times 77, this is going to give us a value of 0.0393 gigapascals. And you can convert this to megapascals if it's a little bit cleaner, and that's going to be 39.3 megapascals, right? Just multiply it by 1,000 to change it to megapascals. Okay, so if we do that for this guy, that's going to give us the value of 78.5 megapascals. And lastly, down here, again, we'll do the exact same thing, times 77 gigapascals. And we're going to find that we get 0.118 gigapascals. And that works out to be, just multiply it by 1,000, 118 megapascals. Now, it turns out that we can also calculate shearing stresses due to torsion using these equations here. And we call these the elastic torsion formulas, where T is the internal torque. Rho here is the same rho that we were using in this expression, just the radial distance out from the axis of the rod. And J here was the polar moment of inertia, which, if you recall, in the last video, we already calculated here as 1.272 times 10 to the negative 6 meters to the fourth for this particular rod. And then here for max shearing stress, we just substitute in rho for C, and C is just the maximum possible radius that we get of this rod. So let's go and solve for the shear at a distance, the shearing stress at a radial distance of 10 millimeters out from the axes. So we'll do shear at 10 millimeters. Well, our applied torque was 5 kilonewton meters, and the distance here that we're working with is 0.01 meter, right? That's just 10 millimeters. And we want to divide that by J, and we set up here that J was 1.272 times 10 to the negative 6 meters to the power of 4. So let's write that down. Now, if we look at these units, this isn't super intuitive about what kind of units these are going to give us. So what you might want to do is you might want to just adjust it a little bit. So we will get 5 newtons times 0.01, and this is over 1.272 meters squared. And this 10 to the 3 divided by 10 to the minus 6 is going to be equal to 10 to the 9, which we can just leave on the top. So just like that. And now we can see that when we do this calculation, that we're going to get actually 39.3 megapascals. Or another way that we could have got to this is we could have just done 5 times 0.01 divided by 1.272, and this was newtons per meter squared, and we would have been left with 0.0393 times 10, and we'd have to put this back in, so 10 to the 9, and this is in units of pascals. And when we see pascals times 10 to the 9, that's gigapascals. So this is also the same thing as 0.0393 gigapascals. And you can convert gigapascals to megapascals by just multiplying by 1,000. So that would, same thing, that would yield exactly the same answer. We'd get 39.3 megapascals. And let's compare this to what we said we got up here. Where were we? So when we just multiplied our shearing strain by the modulus of rigidity, we got 39.3 megapascals. And when we used our elastic torsion formula, we also get 39.3 megapascals. So that's pretty cool. That's a good check. Let's go and do the shearing stress now for the radial distance here out where rho is equal to 20 millimeters. So we'll do the shearing stress for rho when rho is equal to 20 millimeters. And we're going to get, we'll use the exact same formula. So we have T times rho over J. And that's going to give us 5 kilonewton meters times 0.02 meters times, or divided by J here, and again that's 1.272 times 10 to the negative 6 meters 4. And what we could do is we could skip all this unit stuff and we could just look and say, hey, well, when we multiply kilonewton meters by meters and divide by meters to the power of 4 times 10 to the 6, negative 6, that's just going to return us a value that is in gigapascals. So if we just do 5 times 0.02 divided by 1.272, that gives us the answer of 0.0786 gigapascals. And we can convert that to megapascals by just multiplying by 1,000, and we get 78.6 megapascals. Now, if you can remember that confidently on a test, that's okay. You can jump to that conclusion, and if not, make sure you check all the units and you get a sensible answer. And when we look up here, so when we compare this to what we did up above, 78.5 megapascals, 78.6. That's just due to some rounding errors, but that is definitely the same answer that we were expecting to get for shearing stress at that location. All right, and so now let's just, while we're at it, let's just go and just calculate the last one here. We want to calculate the maximum shearing stress, and this is where we're using C, and so we have tau max is equal to our T times C over J. And again, this is where rho is just maximum, and that is where rho is equal to 30 millimeters. So we're going to drop all this stuff in. Again, we get 5 kilonewton meters. It's getting a little bit repetitive, but I think you guys get the point. And 0.03 meters over J, and that gives us 0.118 gigapascals, which again we can reduce, or we can convert to 118 megapascals. And exactly that is what we were expecting when we just multiplied the shearing strain by the modulus of rigidity here and got 118 megapascals. Shearing stresses in hollow circular members that are experiencing torsion. So we're going to use the same formula that we were using for solid circular members, which was the shearing stress is equal to that internal torque times rho, which is our distance out from the very center of the axis, out radially, and this is over J, the polar moment of inertia. Now the only thing that's changing is for values of rho that are less than C1, so C1 here is our inner diameter, and C2 here, or inner radius really, and C2 is our outer radius. So for values that are smaller than our inner radius, there'll just be no shear because there's no material there to be in shear. And then we'll experience shear that increases linearly from a radius here, or a value of rho of 15 millimeters out to 30 millimeters. And if once you find the max shear, if you basically just extended it back down to the axis and set that to 0, you'd have a linear growth, just like we were having the solid circular shafts, just where the minimum shear will be a non-zero value, but it'll be on that linear scale, basically, of increasing shear with this increasing distance from the axis. So to get started, let's figure out what our polar moment of inertia is, and our formula is pi over 2 times c2 to the power of 4 minus c1 to the power of 4. So where we were dealing with solid circular rods, we were just setting c1 to be equal to 0 and then going like that. But in this case, we actually have a value for c1, so now we have pi over 2 times c2 to the power of 4. So this is 0.03 meters to the power of 4 minus 0.015 meters to the power of 4. And when we crunch that, we basically just get this is equal to 1.193 times 10 to the minus 6 meters to the power of 4. All right, so now we can go ahead and calculate our shear, our max shear. So let's do that one first. So for max shear, we're going to have 1.5 kilonewtons. Oh, sorry, 1.5 kilonewton meters. That is our internal torque, and then we have 0.03 meters. Right, because we know that our shear, our max shear, will occur at that max distance at C2, so we plug in C2 there, and then we throw this all over J, which was 1.193 times 10 to the minus 6 meters 4. And it turns out with these exact units, if you have kilonewton meters times something times 10 to the negative 6 meters 4, well, if you just do 1.5 times 0.03 divided by 1.193, we're going to get this number here, which is 0.0377, and this unit is in gigapascals. And we can convert that to megapascals by just multiplying it by 1,000, which is 37.7 megapascals. All right. Now, if you're not comfortable making the jump from these units to gigapascals, or you can't remember why that works, this is all the units, and this is how we get to 0.0377 gigapascals. All right, so that was our expression for Tmax, or our equation for Tmax, where we had T times C2 over J. Now, to get our Tmin, we have very similar. We just have T times C1 over J. So if we plug in these numbers again, we just get 1.5 kilonewton meters times C1, which is just 0.015 meters, and that's all over J, which was 1.193 times 10 to the negative 6 meters 4. And if we just do that equation using the same logic that we had here, we're going to find out that this is 0.0189 gigapascals. All right, and that is equal to 18.9 megapascals. So this is the shear that we're basically feeling on the inner wall here, which happens to be our minimum shear. Now there is another way that we can calculate minimum shear. Maybe let's change the color. The other expression for minimum shear that we can write is tau min is just equal to the ratio of C1 over C2 times the maximum shear. So in this case, we know the maximum shear, we know C1 and C2, so we have C1 is 0.015, C2 is 0.03, and the shear, the max shear was 37.7 MPa, and if you just run that, you're going to find out that we get 18.9 MPa, which is exactly the same. And what that shows is that if C1 approached 0, then our minimum shear would approach 0. So we are getting that linear decrease in shear as we go from the outer surface in towards the radius. And in a case of a hollow shaft like this, it'll reach its minimum shear when it hits that inner wall. But if that inner wall went all the way to the middle, then we'd have a solid circular shaft, and then these formulas would still basically hold true.